theorem, and it is very important and expected one. Suppose f is bounded on closed interval ab and f has only finitely many points of discontinuities on this closed interval ab. Now here a and b may or may not be the point of discontinuity, we don't know, but on this interval, closed interval, it has finitely many points of discontinuities. And alpha is continuous at every point where the function is discontinuous, right? And I have to prove that f is Riemann integrable on closed interval ab. So it is a step-by-step proof. It is very important to consider every step. Let's start with the proof. Let epsilon be positive. Let's take this. And let me define m to be equal to, it is very a special case. So I'm defining this m to be equal to supremum of mod of fx on this closed interval ab, and let E be the set of points at which f is discontinuous. Since E is finite and alpha is continuous on E, so let me define this set E to be finitely many points of discontinuous. Let me write all those points where the function is discontinuous. So let's suppose that it is C1, C2, C3 up to so on, and it's up to, let me take Cj and then Cn. So these are finitely many points and alpha is continuous at every point. Now first step, consider this step, mind this step. Now because E is finite, so we can cover E by finitely many disjoint intervals, right? Uj, Vj, let's suppose that, which is a subset of closed interval AB, such that here if you look at the figure, this is your closed interval AB and these are blue colored points. These are the points of discontinuities, right? Your set E, C1, C2, Cj up to so on. And these red colored are these small disjoint intervals which are covering these points. What I'm going to do is I have to remove all these points from this interval. I'm going to remove all these points from the interval, but I will not remove the points, I will remove the intervals containing these points, right? So that this closed interval will be free of all the points of discontinuities, right? Okay, so we can cover E by finitely many disjoint intervals, this Uj, Vj, which is a subset of closed interval AB, of course, such that summation of, because alpha is continuous at all these points, alpha of Vj minus alpha Uj, taking this sum over j, this sum should be less than, strictly less than that epsilon which I have chosen, right? And kindly remember that their lengths have been settled, that is less than epsilon, okay? Now the second step is, furthermore, we can place these intervals in such a way that every point of E intersection open interval AB lies in the interior of some Uj, Vj. Of course, because what is E? E is a set of all these blue colored points, right? If I take their intersection with open interval AB, why I have used here open interval? Because it's not mentioned that A and B are points of discontinuity or not. It's not mentioned, right? So A and B may or may not be the points of discontinuity. That's why I have taken the open interval where A and B are not included. So if I take the intersection of E with this open interval, of course, every point will lie in some of these Uj, Vj, right? Okay. Third, now I am going to remove the segments Uj, Vj, open intervals. Not these are the closed ones, but I have to remove the open intervals from this closed interval AB. So Uj, Vj remains in the interval. I'm just removing this open interval, that is this part. I'm removing this part, right? So U1, V1, U2, these all are remained in this closed interval AB, right? Here it's clear? Okay. Now what is the remaining set will be? The remaining set, let's name after removing all these open intervals uj, vj. So the remaining set left, name that as K, and that will be compact. Now what is K? K is the union of all those disjoint closed intervals, of course. First one is your A and U1, right? From this A to this U1. Second union, then this is removed from this closed interval AB. Then I will take V1 and U2, okay? V1 and U2. And then this will be removed. C2, the point of discontinuity with this open interval is removed. Then is V2 and U3. Okay, so on. Okay, now this K is compact. Why the K is compact? Here each interval is closed and bounded. Okay, and union is closed and bounded. So therefore K is compact. Now as f is continuous on K, because why f is continuous on K? See, on closed interval AB there are many points of discontinuities. We have removed all those points. Now remaining is K set. So f is continuous on all over K, right? So f is continuous on K because points of discontinuity have been removed. And since K is compact and also K is compact, so what we get, hence f is uniformly continuous. It is a result. This is a result. So f is uniformly continuous on K. Hence f is uniformly continuous on this K. So therefore, now defining the definition for the uniformly continuous. So there exists delta positive depending on epsilon only, such that, yes, mod of x minus y is less than delta, which implies this is a definition for uniformly continuous. F of x minus f of y, this is less than epsilon for all x, y belonging to K. Okay. Now, choose a partition P such that as follows. Now, each uj, vj belonging to P. Of course, uj, all the uj's and vj's are belonging to P. And the open interval uj, vj, which we have removed from that closed interval AB, if I take the intersection with P, then this will be, of course, phi, because these open intervals are already removed from the closed interval AB. So this intersection is phi. And delta xi is less than, this is very important to note, this is less than this delta. Okay. When this should happen, if xi minus 1 is not equal to uj, this is very, very important. Because if xi minus 1 is equal to uj, then if I take their difference xi minus 1, this cannot be equal to delta y, because already I have mentioned, I have settled their length in 1. That is, their sum is less than epsilon. Their lengths have been settled in 1. So this cannot happen. So this delta xi is less than this delta if this is not equal to uj. Okay, next. Now define let mi be. Yes, what we define mi to be equal to? Yes. Let me change the color of the pen. It is supremum of fx on closed interval xi minus 1 xi, and small mi is infimum of fx on closed interval xi minus 1 xi. Then their difference is less than equal to, can I take their difference to be less than equal to twice m? Because m is maximum for all I. I have taken in the very start this capital M. This is equal to supremum of mode of fx. So for all I, it is maximum. So can I write their difference to be less than equal to twice m? Very fine. Okay. So for all I equal to 1 to n. Now since f is continuous on k, and hence on this. If it is continuous on k, of course, then f will also be continuous on this closed interval. Because f is continuous on this closed interval, this segment, of course, f will attain its maximum and minimum on this segment. Whenever function is continuous on any interval, it has its maximum and minimum on that interval. So for this interval, let's consider maximum and minimum. Okay, so for attaining the maximum and minimum for this interval, I have to select SI, any two elements belonging to this interval, such that f of Si is equal to, yes, capital Mi, and f of Ti is equal to small mi. It's your wish whether you want to take Ti first or Si first, it's your wish. Now since SI, belonging to this interval, and I know that whenever two elements belongs to a closed interval, their difference mod is less than equal to difference of this. And that is xi minus 1. Don't have to take the mod because already this is positive. This is equal to delta xi. And we have considered delta xi to be less than delta. So therefore, now whenever this 2 is less than delta, so f of Si minus f of Ti should be less than epsilon according to the definition for the uniformly continuous for f, right? I have mentioned the definition for the uniformly continuous here. So whenever any 2 points mod less than delta, then f of x minus f of y will be less than epsilon. Here I'm having the points Si, Ti. This is less than delta, so f of Si minus f of Ti will be less than epsilon. Clear? Very clear. Okay. Now what is f of Si? This is capital Mi. From here, just now I have written. Okay. Let me take this as star. From star. And what is f of Ti? This is small mi. This is less than epsilon. Their mode. So this implies capital Mi minus Mi is less than epsilon. So thus, I have two values now. Mi minus Mi is less than equal to, yes, from here, 2m. Okay. And also, Mi minus small mi is less than epsilon. I got two statements. Less than epsilon when xi minus 1 is not equal to uj. And less than 2m if you take that the other case if it is equal to uj. You can say like this, right? Most of the steps are just to commit to memory. Next, the last, we have to calculate the value for UPF alpha and LPF alpha, the fifth step, which is summation of Mi minus Mi delta alpha I. Now I have to split up this into summation on, okay, xi minus 1 if it is equal to uj. For that, what is my mi? Mi, small mi will be different, na? Then in that case, alpha I plus, and the summation of if xi minus 1 is not equal to uj. For that, I have to take another value for this accordingly. Okay, fine. Now when xi minus 1 is equal to uj, then mi minus small mi is 2m. And what is delta alpha I? Then in that case it is epsilon plus sum when xi minus 1 is not equal to uj, then this value is epsilon, and delta alpha is, yes, it is alpha b minus alpha a, any real number. Okay, so this is equal to 2m epsilon plus, this is, let me write like this only first. This is alpha b minus alpha a. Taking this epsilon common, 2m plus alpha b minus alpha a, taking this epsilon common, and this is any real number, so this can be written as epsilon dash. I can write this as epsilon dash together. Okay, fine. So UPF alpha minus LPF alpha is less than epsilon dash because epsilon is already arbitrarily chosen to be positive. So epsilon dash is also arbitrary. So therefore F is Riemann integral on closed interval AB because it is the result. Whenever UPF alpha minus LPF alpha is less than epsilon, then F is Riemann integral on closed interval AB. This is if and only if case. Thank you so much for watching this video. And a very important note is over here. I'm just writing that note. What if F and alpha have a common point of discontinuity? Then if F and alpha have a common point of discontinuity, then yes, then F, very good, need not be in Riemann integral, need not be in Riemann integral, right? So thank you so much. Have a very nice and blessed day. God bless you all. Thank you.